Okay, thank you for attendance. The title of my presentation is Blast Response in Non-Smooth Elastic Plastic Hardening Softening Structures. I am from University of Aberdeen lecturer. I am presenting for Non-Smooth Dynamical System 2023 Dublin. The content of my presentation, first I talk about the motivation about this talk, and then governing equations and numerical simulations of elastic plastic hardening softening system in blast loading, representing the simulation for elastic perfectly plastic systems, current code of practice, conclusions and new features of elastic plastic hardening softening system. Little bit about the motivation. Here at top right, there is a part of a blast wall. They are structures that sacrificing layer such that when explosion occurs, they fold and they take the energy of the explosion, they fold and the structure behind them will be protected. But some other structures are also inherently blast resistive. But if not, they are protected by some protective structures like blast wall. This is a one pitch of blast wall, which obviously, when the explosion occurs, it will be deflected. And this is a model developed by finite element about couple of thousand shell elements, which is exposed to explosion. And obviously, each shell element have about maybe 3,000 nodes. Each node 6 degrees of freedom. All together, for example, this structure 14,000 degrees of freedom, which we simulate. And we apply the explosion and the result of the deflection coming after 35 minutes because of the number of the elements. And basically, after 35 minutes, we know how much folding occurs as a result of explosion. But this is high fidelity model. But is it when we had when we didn't have such facilities to use it, high fidelity model like finite element, what we were doing some simplified model. In simplified model means that, for example, we are simplifying the model by one mass and one stiffness, such that only we measure the displacement of this mass. And we are saying that, okay, if the mass is in the middle and the deflection of this point, we calculate and somehow we determine how much this blast wall is folded and what is the damage. So because everything was summarized in 1 degrees of freedom, for example, we summarize this 14 degrees of freedom in high fidelity model to 1 degrees of freedom. So this is why we call it SDOF, single degree of freedom method. Obviously, my talk is about basically based on single degree of freedom, how accurate this single degree of freedom can be. The big existing code of practice is EPP model, means that we have elastic part. The material of this partly elastic, obviously. When the load is severe, it goes to plastic deformation, but it is perfect plastic without resistance. So we have two stage for material behavior. The blast pulse is either symmetric or isocell triangular pulse or linear decreasing pulse. Obviously, for example, any blast pulse has three stages. The first stage is rising the pressure, overpressure, then falling the overpressure, and after that, the blast is ended. So we have three stage here for loading and two stage here for material behavior. Okay, so basically we have uh, six set of equations. So this is why we basically classified as a non-smooth system. Although appearance seems blast loading, which is nothing to do with non-smooth, but non-smoothness comes from these six categories that produces six type of equations. Now, obviously, the title of my talk is this model, which we present here, elastic, perfectly plastic, is not 100% true. It is elastic, plastic, but in plastic, first it becomes hardening and then starts softening, then rupture. Uh, this is a steel behavior, or many other materials behavior are like this. Then obviously this chart we call Biggs chart, by which engineers estimated deflection of the middle of this structure is based on EPP, but I want to investigate if the model is EPHS. Is this chart can be used or not? If not, what are the differences? We want to say if this chart is inaccurate or it is conservative, which is for safety, is useful or non-conservative. All because I am using this new model, which is realistic model. And all is not the high fidelity model. It is just because I want to represent somehow low reduced order model of this structure. And obviously still, if we have in possession or high fidelity software, we use this to see if we have modeled this correctly or not. Apart from that, there are many other reasons, like surrogate models. Okay, now if I go and summarize how this chart is produced, we see here that for elastic perfectly plastic model, for this part, we have three equations. Equations for the rising time, equations for the falling time, and the equation with no blast. And for this part, we have equations for rising time, we have equations for falling time, and we have equations for no blast. So this is the reason we have six set of equations. We can simulate this and obviously calculate the ductility ratio here, either in elastic or here in plastic. And basically we read these values, which we call ductility ratio, which ductility ratio will be read from this curve or from the simulation here that I am doing. Okay, now if we multiply this ductility ratio by maximum elastic deflection, then we can find a deflection by which we compare with the deflection that we have found from high fidelity model with 14,000 degrees of freedom. Okay, now the comparison is done here. And obviously, uh, for example, 52 millimeter from the high fidelity model, 53, 58 millimeter from these equations, and 62 millimeter from surrogate. Surrogate is published in this paper, which says that if I don't want to do this high fidelity model, which takes 35 minutes, or this, which is graphical, there is no, uh, we cannot use it automatically for design purposes or do trial and error on it. It is time consuming. Or if we don't want to write this set of equation as solvable for one case, we just find a surrogate to represent all SDOFs in one formula, which we put in Excel, give two parameters, this parameter and this parameter, and receive the ductility ratio straightforward, the unadjusted. This is called surrogate. It is important these days because we replace either high fidelity model or low order model by some surrogate model such that we use it in digital twins. This is the motivation basically. But my title of presentation here is not surrogate, but it is the elastic plastic hardening. How can this, how this chart will change or surrogate will change if we use another model, which is more realistic. Okay, in a shadow of non-smooth analysis. Okay, now, so now if I go to the uh, background, these equations are straightforward. You have seen all of them, three equations, rising and falling and after blast. And we write these equations, then we summarize it, abbreviated in non-dimensionless form, such that we solve these differential equations. We directly get the ductility, which is written here, okay? And obviously, in either model, EPP or EPSH, so this part is common. We have elastic part. All the systems have elastic behavior. And obviously, the pulse could be non-symmetric, means a rising time is always higher, shorter than falling times. And then after that, that the blast does not exist. This model also by this parameter or alpha, we can use unsymmetrical pulses as well. Okay, this is a non-dimensionalized equation. When we go to the or main part of the presentation, it comes to this. We are saying that this straight line from here to here, perfectly plastic, is not realistic. And the reality is that we have some hardening phase. There is a resistance, although it is not too much big like this. This is very steep, very high steepness. But there are some resistances. And in the softening, we have resistances. Obviously, our equation will change because this is a rupture displacement. This is a maximum hardening displacement. This is elastic displacement. We define two parameters, which is related to hardening ratio. This is softening ratio. These are very big numbers for steel. And this X bar is the ratio of X divided by X elastic, which gives us a ductility ratio, we call it, for steel. This ductility ratio is higher. It could go higher. Other dimensionless parameter is time, is the T divided by TD is the duration of the pulse. And this important parameter is ratio of the duration of the pulse to natural period. This natural period is substantially important, such that if we cannot calculate this natural period for any structure, we cannot do SDOF. This is a lengthy procedure, but it should be done. It should be done to see how high fidelity models are behaving. Okay, because if we examine the behavior and we see something like this, then we can say, okay, this high fidelity model is reliable. We use some supercomputer and obviously generate a lot of data and then find a surrogate, for example. Or uh, we stick with this final element generate data, use surrogate, or we stick with that, use a lot of simulation and reproduce a surrogate to be used in digital twins. Okay, now if I go to this part, I am using this dimensionless parameter such that I get the results that I require. Now, if I go to hardening part, elastic part in both is are common. We know what are the equation. We define a softening parameter. Beta is a very small number. It is about 1%, means the stiffness of the softening part is 1% of stiffness of elastic part. But obviously we want to include it anyway. So the equations becomes one term extra. Here we have one term extra. Here we have one term extra. If I want to non-dimensionalize it based on these parameters that I have explained here, then it comes to these three equations. So I have three equations here, all non-dimensional. Is solve this differential equation directly gives me direct ductility ratio. And I have three equations here for elastic part, which is common, so it's 6 equation. But still I am not finished because this is just hardening. And if I go here, then I choose the softening parameter. Softening parameter is beta S, is very also a small stiffness here, but in negative means it softens in negative part. So this is also a small, about 1%. So, but I include that in the equation. This is the main equations, mass stiffness and equation without damping is ignored. Obviously, is always is negligible in safety analysis. Uh, and if we convert based on the dimensional parameter, is that we see that here all these dimensionless parameter beta S, beta H, gamma S, gamma H, and all of them are involved. The ranges are involved. And obviously now we can do simulation, three equations hardening, 6 equation we showed before, so it becomes 9 equation. Whereas for the other method, existing method, we have 6 equations. Now, what is happening? We can do now or simulations, or this is an existing model, because if we set beta H and beta S equals 0 in these equations and these equations, then we end up, because we ignore the hardening and softening, so we have elastic perfectly plastic, we end up this equation, these three for elastic, these three for perfectly plastic. And obviously, this is at the model our engineers and designers are using. But I want to examine if I include that, what happens. Both fall in category of non-smooth system. If I do this, the results, obviously, as I told you, the softening and hardening parameters for steel is more or less the same as 1%. And the hardening and softening ratios are very big. It is about near 50 45 for steel. And obviously, for a particular load, which is dynamic load factor, 0.65 means the uh, ratio of maximum resistance to applied force is less than 1, means we are in a plastic situation. If we for that we somehow reduce this response curve. In the blast analysis, the response curve will change the shape. Instead of omega divided by omega n is a ratio of the duration of the pulse divided by the natural period of the structure. So this is some kind of uh, change of variables here because it is a short pulse. We don't have vibration. We have a shock. We have a shock and blast. So duration of the blast divided the natural period of the structure. And this is a ductility ratio. Obviously, this is a top curve, which is black, is EPP model. And this is for particular dynamic load factor. For series of load factor here, we have the whole data. Obviously, whole data is gathered in this top curve for EPP model. Basically, is summarizing these summarizes all the data here in all loading here, all the plastic and all the things summarize much more data than this, which practice at the moment engineers are using. So we have this is summarized maybe more in more detail here. But obviously now that I want to investigate if I use this, what happens to the data? Obviously, the curve falls below like that. The curve falls below like that and is always under. And obviously, this is what I was expecting because there is extra resistance here, 1% resistance in plastic part. It is not zero resistance. There is 1% resistance compared to elastic. So this is why this curve falls below that. Obviously, if I gather this, it is a bottom curve. So I want to know if this bottom curve uh, and this chart is compatible or not, that bottom curve, which is belongs to this. Obviously, when my purpose is comparing those, which obviously I have done this comparison here, which is always below. And if I want to examine the conservativeness is not substantial. As you see here, in the low periods, they are almost identical, but in large periods, there is some deviation, but this deviation is not substantial enough such that it affects the economy of the design. But anyway, the other things that happen here, it is to jump here, which is not examined before. I want to examine it. It happens when we have EPP. It happens when we have EPSS. It is the one load, particular load in all loading conditions. You see these jumps here happens, this jump here happens. This jump belongs to this phenomenon. In this particular load and in this ratio, this jump is happening. This is a new thing that I observed. But obviously, my main purpose was examining the conservativeness, uh, not this, but this is extra thing that I have. This is also expected because in every structure we have some jumps, even if we are in shock, not in vibration, the resonance should show itself, but because it is a nonlinear system, it doesn't show itself in one, it shows itself in a different ratio. Uh, Obviously, There is another jump here, and there may be other jumps, so I want to investigate further if this is the only things that I can see. I have examined, basically, if we want to use the top curve, which is developed by the chart, but consider EPSH. Obviously, we use this one, but consider the hardening softening effect. We can calculate the ratio of these two and define something called the correction factor. Correction factor is a correction factor is always one, as you see here, unless in some ratios is less than one. Means that by this correction factor, we can use the chart, which I showed you at the first slide, but multiplied by some correction factor to consider the effect of the hardening softening. This is correction factor. We see correction factor is always one or less. That is obviously we say because is never more than one. We see so these two terrible jumps here, which the violates or law here, and this is related to the resonance phenomena. In the resonance phenomena, the, the ratio, so we have this unusual or odd correction factor here because of here. We have a jump here in about 162, for example. For EPHS model, we have the same jump in 163. And if at this value, I want to calculate the ratio of the thing, we see this is the only case that is more than one. Obviously, this is related, this is an exception, not the rule, because of resonance phenomena. And these jump points in both models are not the same. There is a small, very small drift and makes this unusual conclusion here about the correction factor. But anyway, the main conclusion is this one. That I do here always I see conservativeness. Always this is below this. And obviously, there may be some hidden jumps here that I am not examining. These are two significant ones. So this is why in this curve, in this both curves, I measure the sharpness of the resonances. This is some kind of response, sharpness of the responses in this curve and this curve. The sharpness measurement, I just defined it here. Q, or sharpness of the resonance, the partial derivative of ductility ratio to the dimensionless period, dimensionless duration, pulse duration in constant load. So if I measure this, I categorized all the maximum sharpnesses. And we see that in I picked up the maximum sharpnesses in each load, and I see all the sharpnesses they gathered here. The maximum occurs here. There is no other sharpness bigger than this. The others are just the natural, the growth of the response. But this one is growth is unusual related to resonance. This is explaining this part or this point. And for this point, the sharpness is measured here. So I excluded all the other sharpnesses. So I have then two conclusions to make here. One is conservativeness, and one is the sharp occurrence of the sharpnesses, which also is expected. But we see that the drifting point means that the difference between the location of the resistor is not significant. It's a couple of percentage of the ratio different, but it occurs in all of them. So this is why I can go to the final conclusion and say, okay, now Uh, First of all, elastic plastic hardening softening material model is described by 9 equations, so it is a non-smooth piecewise linear system. The last four designated can be designated by unsymmetrical, non-smooth triangular pulse in three different time ranges. So that is three range material, three range, it becomes 9 equation. Okay, the results are compared with elastic, perfectly plastic, which is the current code of practice. And we want to examine if this current code of practice is justifiable or not. It is not justifiable if the conservativeness is significant. Conservativeness shown here, if this distance is significantly high, this distance significantly high, obviously for design of the blast resistant structure by EPP method will not be economical. So still, because we have conservativeness, it is insignificant, but it is conservativeness is insignificant enough to be safe. So we stay the safe side. We don't develop any other chart for EPSH model. So degree of conservativeness is not significant. But obviously, one of the reason is because the softening hardening parameter is only 1%. But if new materials comes, this may change. If this level of these softening hardening parameters are bigger than 1%, obviously the story completely changes. But at the moment, in all blast resistant structure, we use steel. And for that steel, this level of conservativeness that see here is not significant. So, and the other conclusion, which is also expected, is that particular load at this period ratio, it shows itself. If the other load doesn't show, means that it is not strong enough. But obviously, in both models occurs, the location of occurrence is a little different, but resonance jump in the response curve could be observed. Why in this load is magnified and the other load is not appearing enough, that could be the subject of future research. Thank you very much for listening to my presentation. Thank you very much.